Hello everyone, welcome back to Introduction to Computational Fluid Dynamics. Last session we discussed about forms of governing equations suitable for CFD along with shock fitting, shock capturing and differences between them. So today we are going to discuss another important aspect of computational fluid dynamics, which is behavior of partial differential equations. So coming to behavior of partial differential equations, which is one of the important aspect of computational fluid dynamics. When we discussed about the process of CFD, first we said the developing governing equations. Then the second important aspect of that process of CFD is understanding the behavior of partial differential equations. So today we are going to continue with that. So these are the session outcomes. Let us define what is quasi-linear partial differential equation or quasi-linear equations. Then we discuss about something called as characteristic curve. Then formulate expression for characteristic curve and solve it using various techniques. So let us consider governing equations. So we have considered governing equations are either in integral form or partial differential forms. These are directly obtained from control volume or infinitesimal element respectively. So integral forms are always from control volume approach and partial differentials are from infinitesimal element, which are always conservative forms. So it is to examine some mathematical properties of this partial differential equations. So to understand the solution approach. So what is the use of this mathematical behavior prediction or identifying is that which approach I can implement so that I can end up with a proper solution. So which is the best suitable approach to solve those kind of equations. So any partial differential equations, if you observe all the governing equations, let it be continuity equation, momentum equation or energy equation, there are no products or exponential in the given equation. They are either partial differential equation of first order, all of them are partial differential equations of first order. So there are no higher orders or there are no mixed derivatives. So I can say that all the derivatives occur linearly based upon that. So the equations whatever we are coming across from continuity, momentum or energy equation, or else the form of equation we earlier considered, that is dou u by dou t plus dou f by dou x plus dou f by dou g by dou y plus dou h by dou z equals to, right. So if we consider that form of equation, even that has only partial differential equations of linear order, that is dou u by dou x, dou v by dou y, dou v by dou z, that is first order differential equation. So we can say that all of them are linear equations. So such linear equations we call them as quasi-linear system. So there are no higher order terms, rather every equation of every term in that equation is of first order derivative and occurs linearly. We call them as quasi-linear system. So these quasi-linear systems are based on, by definition, they are almost linear. They may not be linear, but they can be represented with a linear set of equations. So let us consider same thing. So general quasi-linear system of equations are represented by this. This is for two-dimensional conditions, that is A1 dou u by dou x plus B1 dou u by dou y plus C1 dou v by dou x plus D1 dou v by dou y equals to F1. So since we are considering system of equation, let us consider another equation, that is A2 dou u by dou x plus B2 dou u by dou y plus C2 dou v by dou x plus D2 dou u by dou y equals to F2. See, these are not exactly representing the flow equations, but they are a set of general quasi-linear equations which we come across in the mathematics. So here u, v are dependent variables and u, v are functions of x and y. U is function of x comma y, v is also function of x comma y, and these are these are not independent, rather they are independent variables. And a, b, c, d and f are coefficients which may be functions or may not be functions of x, y and u, v. So these are coefficients, simple coefficients which can be functions of x comma y or u and v, any of them. So how to solve these set of equations? To understand that, let us consider a point in space P. So this point P represents an arbitrary point in the space, and ds represents the direction in which the fluid is moving, and then dy by dx is the slope of that particular curve. So here let us discuss something about indeterminate and discontinuity in the domain. So point A and B, C and D is the point P is intersection of A and B and C and D. C, A, B and C, D are two different curves which are passing through point P. Now there exists an arbitrary curve, you can see E and F. There exists an arbitrary curve on which the solution for point P or solution for those linear set of equations is not possible. That means it is indeterminate. So derivative of u and v are indeterminate at this point P for curve E and F. So this curve E and F is nothing but the discontinuity in the region. So this discontinuity or the curve which indicates this discontinuity, we call it as characteristic curve. So it is a curve on which you don't have a solution, you don't have a proper solution for the given point. So to find such lines, we use u and v. Let us define first. So as we already mentioned, u and v can be represented as the partial derivatives, where you can use chain rule for representing u and v. So u and v can be represented as du is equals to dou u by dou x into dx plus dou u by dou y into dy. Similarly, dv can be represented with dou v by dou x into dx plus dou v by dou y into dy. So du and dv is our solution. Identifying the solution is what we are expecting from this, but for this particular curve E and F, the values of du and dv will be indeterminate. That is, you cannot even have 0 as the value. So it cannot have a finite value, rather it has to be infinity or indeterminate, something like x by 0, which cannot be determined. So these kind of values we are expecting for this particular equation. So this EF is called characteristic curve, where the solution is not possible for the given curve. So now let us rewrite the form of equations. So there are 4 equations now. First 2 where a1 dou u by dou x plus and so on. Then we have those 2 equations plus these 2 equations, total 4 equations. How can we write these 4 equations? So in matrix form, if you go to the previous equation, that is system of linear equations, you can see a1 dou u by dou x, b1 dou u by dou y, c1 dou v by dou x, d1 dou v by dou y. So similarly these 2. Now if we consider the second set of equations, which is dou u by dou x, du equals to dou u by dou x into dx plus dou u by dou y into dy, and dv equals to dou v by dou x into dx and dou v by dou y into dy. So now we have total 4 set of equations. Now if you consider dou u by dou x, let's say similar to what we have done in the earlier case, where we tried to combine all the equations like continuity, momentum, and energy equation and written them in matrix formation, in matrix form, so that we can solve for all 3 equations simultaneously. So similarly, let us apply the same methodology here. So see, A1 dou u by dou x, B1 dou u by dou y, C1 dou v by dou x, D1 dou v by dou y is equals to what? F1. Similarly, A2 dou u by dou x, B2 dou u by dou y, C2 dou v by dou x, D2 dou v by dou y equals to F2. Now let us consider second set of equations. What are second set of equations? du equals to dou u by dou x into dx plus dou u by dou y into dy. So what is the quotient of dou u by dou x? Dou u by dou x is dx. Similarly, dou u by dou y equals to dy into dy. Dou u by dou x, dou u by dou y, and there are other terms? No. The other terms are 0 plus 0 equals to what? du. Similarly, in case of dv equals to dou v by dou x dx plus dou v by dou y dy plus 0 0. So now dou v by dou x into dx, dou v by dou y into dy is equals to du. So this is how we represent these equations in mathematical form. So now let us try to solve this. The solution of this matrix, where we can call this as matrix A is called quotient matrix, and what I want to calculate is, let's say, dou u by dou x. This is called variable matrix and this is called solution matrix. Or so I want to find out the solution for this particular matrix, dou u by dou x. So for that, let us consider A equals to this. Now when we consider matrix solution using Cramer's method, we know that if I want to find the element of solution for first element, then I should replace this with the first row. Similarly, if I want to find solution for second element, then I need to replace the second column with the right side column. So I want to find out solution for, let's say, dou u by dou x. So for that, I need to replace the column matrix here, that is A1, A2, dx 0 with F1, F2, du, dv. Now let us assume that matrix to be B. So I replaced this row here. So F1, B1, C1, D1, F2, B2, C2, D2, du, dy 0, 0, dv 0, dx, dy. So this is my matrix. Now if I want to find the solution for dou u by dou x, how can I find dou u by dou x? Dou u by dou x is equals to mod b by mod a, or determinant of b by determinant of a. So that is the solution what I get. Now in order to predict the characteristic curve, this value should be indeterminate. That means for this value to be indeterminate, mod a or determinant of a should be equals to 0. Determinant of a should be equals to 0. So let us try to find out determinant of a. Hopefully I understood that. So because I'm trying to find out the characteristic curve for this particular set of equations, the determinant of A should always be 0. If mod B or determinant B by 0 is always infinity, you cannot determine the solution. So because of that, I'm considering determinant of A equals to, now as I said, let's use characteristic curve. For that, determinant A equals to 0. How do I find determinant A? So to calculate determinant of A, first you can say A1 into determinant of B2, C2, D2, dy 0, 0, 0, dx, dy. Again, determinant of this is B2 into 0. So A1 into B2 into 0 minus C2 into dy square, B2 into 0, C2 into dy square minus 0, next d2 into or plus d2 into dx dy. Similarly, I can do it for rest of the terms, like a1 into this a1 into determinant of b2, c2, d2, dy 0, 0, 0, dx dy minus b1 into what is the matrix for b1? b1, if I cancel these rows and columns, a2, c2, d2, dx 0, 0, 0, dx dy. Similarly, plus c1 into, for c1 it has to be these three, that is a2, b2, d2, dx dy 0, 0, 0, dy minus d1 into minus d1 into just this row a2, b2, c2, dx dy 0 and 0, 0, dx should be equals to 0. I hope everyone knows the procedure to calculate determinant of this matrix. So when we calculate determinant of this, we'll end up with the equation so if I find the determinant of this particular matrix, then I'll end up with equation as a1 c2 minus a2 c1 d square dy square, a1 d2 minus a2 d1 plus b1 c2 minus b2 c1 dx dy and so on. So this is the equation what we are going to come up when we solve for that determinant. Now divide throughout with dx square. So this will become dx square. This will become dy by dx. X is cancelled. This x square will be cancelled. So now you have a quadratic equation in form of dy by dx square or a dy by dx square plus b dy by dx plus c equals to 0, where a is equals to this part small a and b is equals to this and c is equals to this. So let us consider that. So hopefully you understand what is the equation now. So a b c, if we assume a b c as this, then I can rewrite the equation as a dy by dx whole square plus b dy by dx plus c equals to 0. So this is a quadratic equation. Quadratic equation with function as dy by dx, with variable as dy by dx. So here the intention is to calculate slope of the curve. So slope of curve is given by nothing but dy by dx. So to find the slope of the curve, slope of the characteristic curve, because if mod a equals to or determinant of a equals 0, this condition represents the characteristic curve. So I want to find slope of this, that means dy by dx for that particular characteristic curve. So the solution for dy by dx can be directly obtained. It is minus b plus or minus under root of b square minus 4ac by 2a, which is nothing but dy by dx. Direct solution for quadratic equation. This is general formula which we come across for solution of quadratic equation. So dy by dx is equals to minus b plus or minus b square minus 4ac by 2a, where d is the discriminant, which is equals to, or d square, or d is equals to b square minus 4ac. Based on the value of this d, which is discriminant, the nature or behavior of the curve can be estimated. Or indirectly, when we are solving for set of quasi-linear equations, we are considering those quasi-linear equations to be the flow field equations. So indirectly we are trying to identify the general behavior of the flow. So this nature of the flow or behavior of the flow can be identified or can be predicted based on the discriminant value, which is b square minus 4ac. So if d is greater than 0, then dy by dx is having two distinct roots which may be equal or which may not be equal, but they have two real roots. So the characteristic curve will have two distinct regions. So the solution for point P of that particular case will have two characteristic curves. So number of characteristic curves for each. Let's say if it is having two roots, that means two characteristic curves, and such kind of flow or equations we call them as hyperbolic equations. Such system of equations we call them as hyperbolic equation. Now if d is equals to 0, you have only one root for dy by dx, that is minus b by 2a. In that case you have only one characteristic curve. These kind of equations we call them as parabolic equations. The system of equations which exhibit these kind of roots, we call them as parabolic equations or parabolic in nature. Now third case, when d is less than 0, that means d is minus, d is on negative end. So the roots are complex or imaginary. The roots are imaginary. For these kind of equations we call them as elliptic equations, and you cannot predict proper characteristic curves. They are not real characteristic curves. The real characteristic curves cannot be determined, rather they will be imaginary in nature as the nature of roots suggest. So that is the end of the session. So today we have discussed about forms of governing equations, followed by implementation of Cramer's rule to study the behavior of a particular linear equation, that is set of quasi-linear equations, and we have classified the behavior of linear equations or quasi-linear equations based on the nature of the roots, that is the solution obtained from the Cramer's rule, and nature of the roots what we have observed, that is parabolic, hyperbolic and elliptical in nature. So that's all for today. Thank you very much.